In this video, we cover chapter 4.8. So we are going to be looking at examples for applications of vector spaces. Our learning objectives are to use a determinant known as the Wronskian to test a set of solutions of a linear homogeneous differential equation for linear independence. So we're going to have a method using the determinant to check to see if equation is independent or not, if it's a linear homogeneous differential equation. And we are also going to learn how to identify and sketch the graph of a conic section and perform a rotation of axis. So our first video is going to cover linear homogeneous differential equations and the Wronskian method to test. And our second video will cover conic sections and how we rotate axes. So let's review linear differential equations. You learned about these in calculus. So a linear differential equation of order n is in this form, where you have y to the nth derivative. So at some point, instead of putting n, dash, dash, dashes for the nth derivative, we put an n up there in parentheses. And then the next term would be a function, we call it g n minus 1 of x multiplied by y to the n minus 1 derivative of y, all the way through g1 of x multiplied by the first derivative of y, and then what we call a function g naught of x multiplied by y. And so that's our linear differential equation of order n. And so g naught, g1 through gn minus 1 and f are all functions of x, with a common domain. And then if f of x equals 0, the equation is known as homogeneous. Otherwise, we say it's non-homogeneous. And a function y is a solution of the differential equation if the equation is satisfied when y and its first n derivatives are substituted into the equation. So let's take a look at an example here. So we are going to determine which functions are solutions to this linear differential equation, x y second derivative, or you might call it y double prime, plus 2 times y first derivative, or you might call it y prime, equals 0. So this equation is equal to 0, so it's known as a homogeneous linear differential equation. It's linear because we don't have any exponents here. Our highest power of all these terms is 1. So let's check. So our first check here is going to be if y equals x, then y prime is going to be 1, and y double prime, the second derivative, is 0. So if we plug those values into the equation, x times 0 plus 2 times 1, that's 2, so it's not 0. So y equals x is not a solution. I'll cross it out with a big X here. Our second function we're going to check is if y equals 1 over x. And so then the first derivative is negative 1 over x squared. Remember, when you take derivatives of 1 over x, you rewrite it as x to the negative 1 and then apply the power rule. So that's where the negative 1 over x squared comes from. It'd be negative x to the negative 2 after we apply the power rule. And then we rewrite it in this form here, negative 1 over x squared. The second derivative, y double prime, is 2 over x to the third power. So remember, if you're doing the derivative again, that would be a negative 2x to the negative third power by the power rule, but then we would write it, and there's already a negative in there, so then we would write it as positive, because of double negatives, 2 over x third. You could also just say 2 times x to the negative 3. So plugging in our values, we're going to have x times 2 over x to the third minus 2 times negative 1 over x squared. Those are actually going to cancel, so that gives us 0. So we say that y equals 1 over x is a solution, so we'll circle that one. And then we'll check our next function if y equals x times e to the x. So the first derivative using the product rule there is going to be x e to the x plus e to the x. And then the second derivative is going to be x e to the x plus 2e to the x. You'd use the product rule on the first term there and then combine like terms. So if we plug these values in, we're going to have x times x e to the x plus 2e to the x plus 2 times this quantity x e to the x plus e to the x. So you can see here, we're not going to get cancellation. We're going to have an x squared from these first terms here. So this is not a solution. So we'll cross that function out. So not a solution to our linear differential equation that we are given here. And then the last function to check is x e to the negative x. So again, using the product rule, our first derivative is going to be e to the negative x minus x e to the negative x. And then our second derivative, using the product rule again and combining like terms, is going to be x e to the negative x minus 2 e to the negative x. So then plugging in our functions for the second derivative and the first derivative, we see, again, not 0. We're going to have an x squared term that's not going to cancel out, and some other terms that might not cancel out. So x e to the negative x is not a solution. So we found only the function 1 over x is a solution to our given linear differential equation. So here is a general explanation of solutions of linear differential equations. So every nth order linear homogeneous differential equation has n linearly independent solutions. So moreover, if y1 through yn is a set of linearly independent solutions, then every solution can be written as a combination of those. So every solution can be combined as a combination to give us y. So we can always write y equals c1 times y1 plus c2 times y2, where all of those y1 through yn's are solutions of the linearly independent solutions of the linear homogeneous differential equation. And then the c's are real numbers. So c1 through cn are real numbers. And then there's an important remark over here. So make sure you notice that the solution in this form y equals c1 times y1 plus c2 times y2 all the way through plus cn times yn, where the y1 through yn are these linearly independent solutions for our homogeneous differential equation. This is known as a general solution of the differential equation. And you probably saw this in calculus. If not, you could skim back through a calculus book if you wanted more details about it. So now we're going to use what's known as the Wronskian determinant. So we define the Wronskian determinant for a set of functions. So we're going to let y1 through yn be a set of functions. And then each of these has n minus 1 derivatives on an interval I. And so the determinant takes all of the functions and their derivatives in the respective columns through the nth minus 1 derivative here in the last row for each of these functions. And the determinant of those functions is known as the Wronskian. And the Wronskian of a set of functions is named after this Polish mathematician, Joseph Maria Wronski, who lived from 1778 to 1853. So you can read more about mathematician Wronski on Wikipedia. So the Wronskian gives us a method for testing for linear independence. So if we let y1 through yn be a set of n solutions of an nth order linear homogeneous differential equations, so these are our solutions for the nth order homogeneous differential equation, then this set is linearly independent if and only if both directions, if and only if the Wronskian are identically equal to 0. So what the Wronskian gives us is a way to check if solutions are linearly independent or not. And it's important to note that this test does not apply to an arbitrary set of functions. So each of the functions y1, y2 through yn must be solutions of the same linear homogeneous differential equation of order n. So you can't just pick out an arbitrary set of functions and check to see if they are linearly independent and use the Wronskian. The Wronskian is only a test for linear independence when the functions are all solutions to an nth order linear homogeneous differential equation. So they have to be solutions of the same equation, same differential equation. Okay, so we're gonna test this out. We're going to find the Wronskian for this set of functions. And then we're going to see, well, is this set linearly independent or not? So our first function is e to the negative x. So the first column of our determinant is all the derivatives. So e to the x is our favorite function. E to the negative x might be our second favorite function because its derivatives are just e to the negative x and negative e to the negative x rotating, because each time we take a derivative, we get a negative sign that'll change the sign from positive to negative and back and forth. Then our second term in the Wronskian, or in the set of functions that we put in the second column of the Wronskian, is x e to the negative x. And so we know we would use the product rule to find the derivative of this function. So you can see, if you go back to where we were doing the product rule in our example here, part C, you can see we wrote out some of the derivatives here of x e to the x. So you can see that our derivatives would be similar formed. Oh, this is actually x e to the negative x, which was the fourth function we tested out here in our example. So you can see here is the first derivative is e to the negative x minus x e to the negative x. So you could see how we would factor out the 1 minus x and multiply this by e to the negative x. My handwriting's not so great there. And similarly for the second derivative. So you can see here where this second column is getting values from. The third function is x plus 3 multiplied by e to the negative x. So it's similar, but you've got that extra plus 3 that's going to come up in your product rule. And so you can verify these calculations for the first derivative and second derivative. And so when we're calculating the Wronskian, you might notice each one of these has e to the x in it. So we factor out here e to the negative 3x. And we do that because of the exponent property when you are factoring out of determinants. If you go back to theorem 3.6 in section 3.3 about properties of determinants, you'll see examples where we factored out like 5s and 10s. And so in 3x3 matrices, when we factored those out, we factored out 5 to the third if we were factoring a 5 out of each row of the matrix, or 10 to the third if we were factoring a 10 out of each row of the matrix. So that's why we've got e to the negative 3x here, because we're factoring e to the negative x out of 3 rows here of this matrix. So you can go back to section 3.3 to see some examples of that if you're wondering, why did we take out a e to the negative 3x and not just an e to the negative x? It's because this is the 3x3 determinant, and we have this property when we factor out of determinants, we get the exponents. Okay, so then doing some simplification here, we see this just becomes this more simplified determinant through row. I guess we could do row reduction there, or just think about how the different factors are multiples of one another. But it looks like this is just row reduction to try to get some of those x's out in rows 2 and 3 that we got to this step. And so this equals 0. So you can work out and expand each of the cofactor expansions here and verify that you get 0. So because this equals 0, the Wronskian is identically equal to 0. And so any value of x is going to give 0 for our determinant value here. So we say the set of functions is linearly dependent. Let's go ahead and do the cofactor expansion here of our determinant so that we see exactly why we're getting 0 there. You don't have to check this every time. You can use SIMPy, although with symbolic functions like x, you may want to do it by hand. So let's see, in our cofactor expansion here, I'm going to have 1 first times the determinant of 1, -2, and 1, -2. So remember when we do the cofactor expansion, because I've chosen 1 from this first position, then I'm using the values that are in the other rows and columns. So that's the 1, 1, -2, -2. And then I'll move on to the x, which is going to give me, okay, and then I have to think about x is in position row 1, column 2. So that's going to give me a negative. It's going to be minus x times the determinant 0, 0, 1, -2. And then x plus 3 is in row 1, column 3. So that's going to give me a -1 to the 4th. So that'll be a plus here. If you remember back to when we did cofactor expansions. And this will be 0, 0, 1, and -2. And then you can check if we do each of these determinants. Okay, this determinant here is going to be -2 and then minus -2. So -2 plus 2, that's 0. This determinant here is going to be 0, minus 0. And this determinant here is going to be 0, minus 0. So you can see from the cofactor expansion why this all equals 0, even though we've got the e to the -3x out front. Each cofactor expansion gives us zeros here. So it's going to be e to the -3x times 0, which gives us a 0. So that's why we're able to conclude that this determinant equals 0 and the set of functions is linearly dependent. Okay, let's look at our next example. So now we're going to look at these set of functions, 1 e to the x and e to the 2x. And we're going to figure out is the set of functions linearly independent or not. So we're going to set up the Wronskian. So here's our 1. All the derivatives of 1s are zeros. E to the x is its own derivative. And then e to the 2x has these derivatives, 2e to the 2x and 4e to the 2x for the second derivative. So then the cofactor expansion is going to work out to be this function here. So you can verify that and then see that this is not identically equal to 0 because values of x exist for which this Wronskian is non-zero. If you plug in x as 0 for 2e to the 3x, you're still going to get a value there because it'll be 2e to the 0. So you're still going to get 2 there. So we get to conclude then that this set of functions is linearly independent. All right, let's go ahead and verify actually the cofactor expansion because it'll be pretty straightforward for us. So if we do that in this blank slide, we're going to be able to make use of the zeros here. So in fact, the only cofactor expansion here that's going to work out is going to be 1 times the e to the x, 2e to the 2x, e to the x, and 4e to the 2x. And the reason this is the only part I have to expand out is because if I take the 1 here, then I've got this area here. And if I take either of the other values, I'm going to get those zeros in there, and it's going to work out to give us 0 determinants for the cofactor expansions if I choose e to the x and e to the 2x. So the only calculation I really have to do here is the cofactor expansion for 1. And so this is going to be, here's our 4e to the 3x that we got, minus on the other diagonal 2e to the 3x. And we're getting e to the 3x because we had e to the x times e to the 2x here. So this is how our simplification works out. So it's definitely doable by hand. Okay, and in this conclusion, as we said, because this is a non-zero determinant from the Wronskian, the set of functions, we get to say these are linearly independent as solutions to linear homogeneous equations. So the next example, we're going to determine whether the solution satisfies the differential equation and if the set is linearly independent. So if the set is linearly independent, then we want to write the general solution of the differential equation. So here's our differential equation, the third derivative of y plus 4 times the first derivative of y equals 0. And here's our set of functions, 1 sine of 2x and cos 2x. And so 1 has derivative 0 for all derivatives. And so if we plug in 1 for the function, then the third derivative of 1 is 0, and the fourth derivative of 1 is 0. So of course that just equals 0 for the 1. Now let's check the sine of 2x. Sine is cyclical, so the first derivative sine of 2x is 2 times cosine of 2x. The third derivative is going to be negative 8 cosine of 2x. And you can verify it. Okay, if we plug those in, the 8s are going to cancel out because there's 4, and so we're going to get a 0 here. Remember, these are the first and third derivatives, not the first and second derivatives, so that's why we got cosine in both places when we were doing the sine derivative. That's also why we got the negative 8, because 2 to the third gives us that 8, and then we get a negative out because of the cyclicness of the sine function. It goes sine, cosine, remember, negative sine, negative cosine, so there's going to be negatives in there. For the function y equals cosine of 2x here, there we've got y equals cos 2x, and the first derivative is going to be negative 2 sine of 2x. We're skipping the second derivative and going to the third derivative, 8 cos of 2x. And because we started with y equals cosine, then we end up positive when we get to that third derivative because we've cycled through the negatives. And so when we plug those in, they do cancel out, and we get a 0 here again because of this 4 here. Okay, so we've shown that this is a solution set for the differential equation. So now we're going to check the Wronskian to see if the set's linear independent. And again, because we've got the zeros here, we can choose 1 and then just the other values in our cofactor expansion. Because if we choose sine 2x, the zeros below the 1 are going to cancel that out. And similarly, if we choose cosine of 2x, the zeros are going to cancel out that determinant. So we just have to expand the 1 times the determinant for what I've circled here in green. And so that works out to be negative 8. You can see if you simplify it and make use of the fact that cosine squared theta plus sine squared theta equals 1. We're just going to have a negative 8 here by Pythagoras, which is not 0. So this set is linearly independent. So now we have to write the general solution. So our general solution, we can think about the relationship between sine and cosine being cyclical. So with our c's being constants, we can say this is a constant plus a constant times sine of 2x plus a constant times cosine of 2x, and we call the different constants C1, C2, and C3. And making those constants, we would know because we know from the work we did up here that we had the constants multiplied by the sine of 2x and the cosine of 2x as we cycled through the cyclical derivative. Okay, in the next video, we're going to take a look at some conic sections and see how we can use rotations with those.